So what we're going to discuss here is the law of the lever with both discrete points and over continuous regions in 1 and 2 dimensions. This is a picture of my man Archimedes. First, let's follow his simplified version of his argument about the development of the law of the lever by recognizing that first, equal weights at equal distances are in equilibrium. This should make sense. This seems kind of obvious that if we hang a weight at the same distance on each side of a balance, that the lever will balance. So we can follow this to also tell us that if we move the weights to the middle of the balance, we'll still be in balance. So but two weights at the end are the same as those two weights together in the middle. That's our second thing to notice. And from that, we can take this further and looking at if we have equal weights at equal distances, again, more of them than two, strung out here, A, B, F, B prime, and A prime, each unit distance between them, we can start applying that rule. These two weights here at A and B, we can put these together at the middle, and it should remain balanced. So now instead of a weight at 1 and a weight at 2, we have two weights at 1.5 or 3/2. And on the right side, we can put this weight at F and this weight at A prime, both hang them at B, and things will remain unchanged as well. And then at 1 unit away on the right, we have a weight of 3. If you notice, the product of this weight and this distance is the same as the product of these weights and this distance. And those things, the product of the weight and the distance, are what we'll call moments. And notice that this is in equilibrium when the moment on the left is the same as the moment on the right. But if we have more than one on each side, then we're going to phrase this a little differently. Now what we're looking for is where the average of the moments would be, an average being the sum of the moments over the total mass of the system. So if we have 3 masses spread out along some sort of lever arm, the center of mass will be where the sum of the moments, the masses times the distance, divided by the sum of the total mass of the system. That's going to be the coordinate. For example, if these masses are of mass 1, 3, and 2, and they're located at 1, 3, and 7 away from the end of the bar, then the center of mass will be the sum of the moments, the x coordinates, and the mass, these distances times the masses, so 1 times 1, this mass 3 times distance 3, this mass 2 times distance 7, over the whole mass, the total mass, which is 1 plus 3 plus 2, so we get 4. And that's exactly where this guy would balance. That's where this would be. So that's the finite case, the discrete case, and if we had a continuous rod of some density, some uniform density, then instead of what replaces our masses is that density in the terms, and instead of the summation, we have an integral. If we're working in 2 dimensions, then we have 2 coordinates. The center of mass, the point has an x and a y coordinate. Those x's and y, the x and y coordinates are found by the moment. The x coordinate is the moment about y divided by the total mass of the system, and the y coordinate is the moment about x divided by the total mass of the system. This is because the thing that's going to have the tendency to rotate something about the x-axis is its y distance. So that's why we're using y here, and similarly x here. So for example, maybe we have mass 1 and a mass 4 at points 1, 0, and 0, 1 respectively. Then the center of mass, the x coordinate, is going to be the sum of the y moments, or 1 times the x distance for this, the moment of this point at 1, 1, 0, and the moment of this point, 4 times 0, the x coordinate. And then we have 1, this mass times the y value, its y value, this mass 4 times its y value, both over the total mass of the system 5, and we get the center of mass at 1/5, 4/5. We can look at this in Python. Just load my standard libraries, tell the Jupyter notebook that we're going to produce the graphs in the notebook. And first I create a figure object. I name it ax because I'm going to add some text to it later down the line, and this is an easy way to add text to the figure object. I plot a single point at 0, 1. I make it a round circle, a blue one, and I make it a little bit bigger because the mass at 0, 1, remember this was our big mass, the 4. Similarly, I'll plot the other mass, the smaller mass, at 1, 0. It's going to be a blue point, and I'll just make it a little bit smaller. The x and y limits, I make -0.5 and 1.5, so just so that we have a buffer around the outside of this, because otherwise it would default to the minimum x and y values in 0 and 1, and we would just have a graph right up on these points, and I want to be able to see the entire region. And finally, I plot the center of mass at 1/5 and 4/5 here, and put a little bit of text below it labeling center of mass. Finally, we want to look at the continuous case in 2 dimensions, but we're still looking at the same things. We're looking at the mass, the moment about x, and the moment about y. Again, though, the moment about x is going to be determined by something about a vertical distance, the length of this vertical strip where these kind of little semi-rectangular regions that we should be familiar with now are formed. This is what's going to cause something to rotate about the x-axis. This is what's going to cause something to rotate about the y-axis. So that's why they are involved in the horizontal. You have a horizontal strip in the y and a vertical one in the x. But if this is the example where we have the origins, the x and y-axis boundaries for this line 4 minus 2x, then we can find the center of mass just by putting these pieces together. The total mass of the system is the area under this curve from 0 to 2, 4 minus 2x. Moment about x is going to be the x coordinate times a vertical strip. Well, the vertical strip is just like that mass. That's how, right, we added a bunch of those vertical strips up to find the area under that. And now for the moment about y, this last piece here, this requires y. Well, so now the width of my rectangle has changed. Now I'm dealing with the width of the rectangle is dy, right? Or we're going to be summing things in the y direction. So I need everything in terms of y. If I solve this equation, y equals 4 minus 2x, if I solve this for x, then I'll get 4 minus y over 2. So that's where this 1/2 times 4 minus y comes. That's the height of this strip, x in terms of y, and then times that distance y, this distance y. So we can, again, do this in Python. We're going to be working symbolically with SymPy, so we create these symbols, x and y, and just to show how to solve an equation for a variable, there's our equation, 4 minus 2x minus y equals 0. Okay, this is a standard form of an equation where everything is on one side and 0 is on the other. But then I can ask SymPy to solve it for x, and I get what I expect, negative y over 2 plus 2. And also, I'm going to go ahead and find my moments. Moment about y is x times that vertical strip, y times that horizontal strip, and the limits for x were from 0 to 2, for y were 0 to 4. And finally, the total mass of the system here, this variable m is just the area under that curve 4 minus 2x from, in terms of x, from x equals 0 to x equals 2. I'll print these out. Total mass. This n is an escape character, so it's just going to hop me down onto a next line, and this will print mx, and whatever that value for mx was, hop down another line, my, and whatever my is, and finally then I'll print the center of mass in the coordinates by dividing my over m and mx over m. Finally, I can plot those points. Again, now I need to change back to working with numbers. So I create my x's as 1,000 evenly spaced points between 0 and 2. And then I create y again as 4 minus 2 times all of those numbers. Create my figure. Plot the x's and the y's. That forms this line. I add a fill underneath to show the region that I'm talking about. So I fill between the x and y coordinates. I lighten it and add a hatch so that I can see. Maybe it just makes it look a little bit nicer. Next, I'll plot a point at the center of mass. Again, I plot it at the x coordinate and the y coordinate. I make it a big point with a larger marker. And I can add a title to the plot, center of mass for the region bounded by, and I skip a line here again with the /n, and by x from 0 to 2, and y equals 4 minus 2x. And again, the dollar signs are just for the mathematics, the typing math into a markdown cell, or into titles. You can always you can use LaTeX in all of Strings and Matplotlib